Okay, welcome back, everybody. Up next, we have Grzegorz and Tomasz from Virtus Labs. They're going to talk about the various use cases that they work with the clients. They have great many experiences. I mean, as well as being the organizers. It's great that we get a chance to hear about their experiences as well. So please, let's give a warm welcome to Tomasz and Grzegorz, and let's hear their presentation.
Hello, everyone. Right, so I'm Gawron, head of data science at Virtus Lab.
And I'm Tomasz Lichoń. Hello, everyone. I work at Virtus Lab as well.
Right, and we want to walk you through some of the use cases that we worked on. So I hope it's going to be useful. It's going to be a little bit of a mix of the business case, so what our clients needed, and then how software engineering helped them with that. As you can see, there is the retailer here. So you think about baskets, buying your products, walking through the store, ordering online. And what I want to, one of the takeaways I want you to have out of, after the talk, is that you don't think about this as a boring stuff. You think behind the basket. So there is a lot of stuff that happens behind this basket. There's lots of optimizations that the companies actually do. Another thing is the big O. Do you know what that might be? Anyone? Software engineering, time complexity of the algos. So this is the big O. But I think it plays very nicely with the big data, because actually it's when the scale is large, those things start to matter. So we're going to go behind those and how software engineering actually helps data science in optimizing the various things that happen behind the basket. So we're going to start with the challenge that the retailers have, how software engineering helps. We're going to go through 3 use cases: warehouse trolley picking, sales forecasting, and Tomek will go through some benchmarking he was doing on the big data. So this is based on our experiences with the clients. There is some things we can say about that and some things we can't. But do ask questions. We'll see what we can reveal. Okay, so let's start with this challenge. What is the challenge? What is the business case? And then we're gonna highlight the need, the business value of the good algorithms. So what you have here is, you are here, and here is some products that are being produced. And for those products to get to you, there is various things along the way that happen. So you have a warehouse, you have a store, there is some vans that bring it if you order it online. Now, what optimization cases there are behind your basket, there is, you can optimize if you go into the store and you have your shopping list. Maybe you just want to buy the stuff that you need in the shortest time available. So this is this picking time, optimizing picking time. And there is various things that you can do to optimize it. You can move the products around the shelf, so just move it to a different shelf. You can move the shelves so that they are located completely differently. There is different spaces for walking. And all of these can impact your picking time. I'm sure you know it's not very nice when, at least that happens to me. Sometimes you go to the store that you know, and you have a plan of how you're going to buy the stuff that you want, and suddenly everything has changed their place, right? So this is a bad example of optimizing picking time, right? So probably the optimization was focused on something else, right? Maybe the sales value. Who knows? But anyhow, we're just going to focus on a couple of those cases. Another optimization case could be that, let's say you have a certain number of vans, and the vans deliver the goods that you order online. So to be able to optimize the usage of vans, that let's say throughout the day from 9 to 5, or maybe in the evening as well, you have the good load on the vans. You need to somehow make sure that people order the goods in the also in the times that does not the time that doesn't suit them very well, and you can do that via prices of delivery slots, for instance. So you make low prices for the delivery slots that no one wants to take, and so on. So there is a lot of optimization there. And the general pattern and use case, and this is pretty general, I guess, is here's your optimization bit. You want to hit that red cross. In order to do that, you change something, change some variables, and then calculate your cost function. Let's say, so here's some cost. We need to have low cost. What you need to, in order to do that, you need to have data, and you also want to augment that data, maybe with some predictions. So just to go through a couple of examples, if you want to optimize the peaking time we talked about, what you can do, you can change the shelf layout so that people have more space to move, or also the products are aligned. The more often, the products that people more often want and need are maybe at the beginning of the store, you know, the various things you can do. What you can do, you can, to augment your data, you can predict the congestion. So let's say, you know, your shelves are very close to one another in a place that lots of people walk through that. So obviously there is going to be lots of congestion, and, you know, your journey through the store is going to take longer. Right, another case would be that there is you want to optimize delivery cost of the goods you ordered online. Then you have, what you can change is, as I mentioned, is delivery slot pricing. Whoops. Okay. Oh, it's enough to say oops. Good. Right, so you have what you can predict. You can predict the route times. So essentially the van would have a route to get your thing from the warehouse to your house. And you might be interested in how long it's going to take to actually get there. So, you know, Friday evenings it might take longer. So you might have a history of your vans, maybe some GPS device logging every minute when the van is, and then you take all of that data and then make predictions on how long the van is going to take to get the stuff to your home. Okay, I'm just going to skip the next one. Because, yeah, I'm just conscious of time. There's quite a lot that we want to go through. Okay, so what is let's just go quickly why software engineering helps in this case in a big way. So essentially, if you're able to improve some algos, you improve the time Oops, no. Oh, yeah, it did work. Okay, if you want to improve your algo, time complexity, for instance, or you are able to parallelize this, what it gains you can get a more precise and frequent prediction, for instance, or optimization as well. And that can give you some optimization improvement. And let's say, even if it's just 1%, if the scale is enough, you have quite a big budget for your software engineering. So thinking about the algos and about the optimization as well. I'm saying software engineering, but really there is a mix between, okay, there is a mix between software engineering and data science here. So optimization, I guess the boundary is not very strict. Right, so let's dive into the first use case that I have here is warehouse trolley picking. Again, this trolley picking example. So we're going to go through what it really is. We're going to go through an approach to optimize it. And this will be using ABM, that is agent-based modeling. This is a very old concept. I guess a lot of people heard about it. So I was also surprised to see that that is actually something that is used, which is pretty cool. You know, again, how software engineering helps in this case. Just to illustrate, you know, this trolley picking problem, you have an empty trolley, you have a shopping list. Hopefully you know what you want to buy. Obviously there is two cases here. There is a store trolley picking where I go to the store and just collect the items that I want, and probably I don't have, sometimes I do have a shopping list, sometimes I don't. But there is another big case where people order stuff online, and in the warehouse, someone has to prepare that package for them. So it can be done automatically, or it can be done in some stores. There is a guy with a basket, a special basket that actually has 6 compartments, let's say, and in each compartment there is going to be one order, and you have like 6 shopping lists, essentially, separate shopping lists. So this is what's happening, and essentially what you want to do, you want to optimize that time from the basket being empty to the basket having all the stuff that you need for the package. So this is the stuff that you want to optimize. Obviously, again, coming back to our example with the store, it might be that the store actually wants you to go around all the alleys, right? And not to optimize the picking time for you. But definitely where there is a warehouse and it is your job to actually pick the shopping list that was ordered online, you do want to make it very quickly, right? So this is a really big component in the cost. Right, so, okay, how that agent-based simulation would work. Here, does it remind you of anything? Any ideas? This diagram? So that's a store, right? So you have the blue shelves. There is some spaces, corridors. That's probably some tills that you pay, right? That's probably where you enter. And these, well, they're supposed to be orange, but okay, these, yeah, these bits here, like yellowish, they would represent congestion. So essentially multiple baskets being more or less at the same time in one spot. So how the simulation would go, it would be, you know, every basket would be an agent, having some rules, and then you run the simulation for lots of agents and see what comes out. You might average it out across various simulation runs to have the, you know, average behavior. We're going to go back to that, how that could work. But just to highlight, again, we want to minimize the trolley picking time for a guy that comes in the shop. And what we can do, we can change the locations of the products or the shelves themselves. So for instance, maybe, I don't know, maybe we want to have a look. Oh, here is, it sounds like there's quite a lot of congestion. Maybe we can move this shelf a little bit to the left, right? So you have some hints, when you draw this, you have some hints as to what the improvement could be. And the great thing about that, I know there was even a project that they were thinking about actually setting up a part of a physical store with some setup because they wanted to test out how it's going to work for the customers. So you can imagine the cost of this, right? So you need to have some part of the shop, maybe it's going to look like a shop, but you experiment physically. So it's a great cost, it's going to take a long time. If you can make it, you know, in silico, so if you can simulate that in a computer, that's really good because you can, you know, move that shelf, quickly have the result and see what's going on, you know, what the improvement is going to be. Okay, right, so agent-based scheduling, what's nice about it is that you define simple rules for your agents, so your basket, so here are 2 agents, right? And there are some simple rules, right? There is many models that you can go for. There is this, what's the name? Force-based models, I think. This is like physical models where you treat those as some physical components, beings that have some attraction forces or forces. Oops, come on. Oh no, I shouldn't say more than oops. It seems. Oh, good. Okay, so there are some forces acting upon those agents, and just simulating the forces, actually you get the behavior of them sort of moving sideways, for instance, right? And why it's nice is that when you run this, you have those very simple force rules, and yet when you run the whole simulation, what happens is that you get a view of how the whole story is going to look like, what your congestion is going to be, where people are going to, you know, have problems going through, that sort of thing. So that's pretty interesting, and it's going to impact your trolley picking time as well. Right, so what would be the process to optimize with agent-based modeling? So obviously you can devise your rules for your agents, but then the very important bit is this calibration of this model that you have to real data. So let's say you accumulate lots of data over time of baskets moving around the store, and then you have your model and you try step by step simulating that model, and you see, okay, does it on average have the same result as your real historical data? So this is what you want to get. So this is really the first step. You need to calibrate. So when you are at the point when you run your simulations and you're getting similar results to how it happened in the past, it's great, because then you can just move this shelf, right? This is what's happening here. You can move the shelf, move the product on the shelf. You can run your simulations, and here you go. You don't need your physical store to tell you what the effect is going to be, right? So this is pretty cool idea. And why it's nice? Oops. Okay. Why? Hello? Maybe I should move around a bit. No. Okay, it's getting worse, it seems. Yeah, I'm not sure. Maybe we need to just connect that directly. What do you think? Okay, yeah, maybe.
Maybe something with this device on the bottom.
Okay, but why I also like this case is that it's a great case for a software engineer, right? Because there is a lot that you can do. You have quite a lot of simulation steps to run, and we're gonna, when we see the slide, we're gonna go through it step by step. But yeah, you can think of how to optimize that, really well, and there is a lot you can do to do that. So I hope by now you do think that there is something more behind the basket than just about, oh, there is a question, okay.
What about the days right before holidays? Don't they skew the data somehow?
But sure.
Or do you take it into the account?
No, it definitely has to be taken into account. So this would be part of the rules that drive your agent, right? Your agent, but not only the agent, the shopping list as well, right? Because that would change what people, there is some seasonality into what you're buying. So yeah, that will have to be like baked in the agent model. Otherwise, you wouldn't be able to calibrate that really to the real behaviors. Okay, maybe we should just do it directly. Yeah. Okay, let me see whether I can go through some other slide maybe next, because this one is actually something that we need to see. But okay, all right, might work. Okay, maybe I should just stand. Oh no, I moved. Okay, but let's go it step by step. So let's say we do want, what we want to simulate is a daily behavior, right, of a people. Let's say we want to simulate, you have these little baskets, agents, obviously imaginary, that move around your store. So over the time of the day, let's say there is like a time step where your basket move is 1 second. So over the duration of the day, you're going to have how many seconds are there in the day? More or less?
86,400.
How much?
86,000.
Excellent. Wow, you prepared well. No, that's the exact number. Over here, I'm rounding that up a bit. That is 10 to 5, let's say a little bit more. So this is how many steps in the day you would have. Then when you want to simulate, you don't simulate one basket, you simulate a certain amount of basket. And let's say, we're going to put it in one store, we're going to have this, let's say 1,000 baskets, right? At the time that are going through the store. That's a lot, right? But okay, let's be a bit pessimistic. Now, you also, once you run your simulation, you want to run more than one, because what you're after the average. You're not after just one simulation, which might be randomized a bit. So that's what you want to do, and let's say you have 100 of those. And then the scenarios or configurations, that would be the configurations that you might be interesting to do. So you move this shelf to the right, that shelf to the left, maybe the products move around the store. So each of those would be one separate simulation. So what you have is, in total, 5, 3, 2, 3, you have about 10 to 13, so one with 13 zeros, steps to do to run your optimization, because that optimization is going to tell you which configuration is best in this case, right? So it's one with 13 zeros, that's quite a lot. I just tested it out on this laptop here, and I have about 100 million operations per second, so let's say it's 10 to 8. So if we wanted to do it on one core, it's going to take you about 1 day, so again 10 to 5 seconds to actually run those optimizations in one box. But the great thing here is obviously you can parallelize that, because it's embarrassingly parallel problem. You know, you have really separate simulations going on, where you can essentially just cut it at this point somehow. And if you had you know, 10 to 5 cores or you know, computing laptops like this, 10 to 5, because there is you know, 100 simulations here and 1,000 scenarios, so that's 10 to 5, then you could do it in 1 second, right? But more realistic scenario is that you have 1,000 cores, and then you can do it in 2 minutes. So it's pretty cool, you know, from 1 day to 2 minutes, just by using some parallelization. Okay, so this would be an example of how you know, how it helps, software engineering helps in a way. We're going to go through how we are actually doing that in one of the next slides. But what I wanted to go through as well is where we go. So parallelization is like sort of easy thing to do. You have to think a bit about the infrastructure to actually run it properly. But here is a little bit more interesting example of where you have to think about your algorithm. So how you actually process your data, what algorithm you choose, so that it is helpful. So this case here is you have, let's imagine this is a map. This is a map of your store that we've seen, right? Oh, here it is. So here's a map of your store. But what you get, let's imagine, obviously maybe not in the normal store, but in a warehouse, there is some tracking device on every basket that tells you where the basket is at a given point in time. And you have this feed, this stream here of the basket points. So this is some snapshot of where the baskets are at a given point in time, but obviously they move around, right? And to do some sort of analysis, for instance, you know, where people go. I mean, you spent 5 minutes next to cucumbers, right? But you didn't buy them at the end because we know at the till you didn't buy them. So this is some sort of information analysis that you could do, would be useful. But for that, what you need to do, you need to somehow map your location in a basket to one of those segments, right? Let's say cucumbers are somewhere here, right? So that would probably be these 2 baskets would be next to those cucumbers. So you have this problem where you have a stream of points coming in. Let's say there is, you know, 1,000 baskets, we say, and daily you're going to have 10 to 5 seconds. So you're going to have, and let's say the location is logged every second. I'm just conscious of time. Try to do it quickly. So you have 10 to 8 of those basket points per day, quite a lot. You have, let's say, 1,000 segments per store. So your store is divided. Let's say more or less these colors would represent segments, some sort of segments in the store. And you want to map those, right? So, okay, what is your algo? Your algo could be very naive and very quick to do, would be you just iterate through all the n basket points. So for every basket point, you go through the k segments and you check, okay, so does the basket point belong to that segment or not, right? And let's say this is just a geometrical thing to check whether it belongs or not. So we're going to say it's O n times k, right? But you can do better, right? You can have a log k for the segments by just organizing the segments in a tree, right? So, and then you can just, in a log time, find the segment that the point belongs to. So that would be a thing. But there's also one more thing you can do. You can actually just cut out the k completely, plus obviously some preparation time at the very beginning. And an interesting way you can do that in is, is if you discretize the space into cells. Let's say the cells would be 10 centimeters by 10 centimeters. And, you know, don't look at those cells because they're pretty huge, right? They contain a couple of baskets, but they should be very small so that it doesn't matter whether you're, you know, in this cell or the cell next to it, you know, they're very small. So if you do that, then you can prepare your map of a cell coordinates to the segment, and then you just take the coordinate of the basket very easily as well in constant time and just look it up in your array because it's just a constant lookup. So essentially then you go through your n basket points, and for every time you just look it up, it's just one time. And I'm sorry, I ran out of time. I did have, just one more thing. There is this, essentially you get it 1,000 times faster, right? So from the initial naive implementation, you just cut out the k, and you have it, because k was about 1,000 in this case, just for one store, you actually have it much quicker, right? So you save a lot of stuff. I wanted to talk about this, but we'll have to take it a little bit after the presentation because Tomek will not have time for his stuff. Okay, so over to Tomek.
Thanks, Greg. So Greg has been talking about some optimizations and parallelizations that you can make in order to improve your algorithms. And I would like to focus more on another important topic, which is benchmarking big data solutions. I would like to tell you more about one case that we had for our client, the motivation for those benchmarks, the tools that we've used, and the profits that we could make for us and for our client. About motivation, it all begins with a question of whether it's better to use open source or enterprise software. Our client has a team of analysts who work on business intelligence tools, and the client wants to minimize the costs of the infrastructure that they use. So these tools may be, for example, MicroStrategy or Tableau, which produce great charts visualizing our data, but underneath they generate SQL queries that we run off top of some SQL solution that is capable of handling those queries and presenting this data. And it may be a relational DB or some computing framework which can compute the results on a cluster. The sample auto-generated query may look like this one, and actually this is the one that we've been benchmarking. It was the sample reference query given by our client to us, and it operated on 6 tables, 3-dimension tables and 3 facts. The dimensions were just calendar, store, and product, and so for each date, for each product, and for each store, we got the information about sales, waste, and stock of a product. And the query simply filtered those data for particular product groups, aggregated it, and presented as a one table. And current SQL solutions was Teradata DB, which is an enterprise solution for which you need to pay a lot. And the query more or less operated on 0.7 billion of rows. Like this was the part of a data set that corresponded to required time range that the analysts were interested in. And I think we We are having some problems, I hope. Okay. And the query took 5 seconds to compute for Teradata. And the question for us for this benchmark was whether if we can do better with some open source solution, for obvious reasons. So we started with some local tests. We've separated a small data set. We took the same query and ran it with commonly known technologies. At the beginning, we thought of more OLAP style solutions like Druid or Kylin, but we found out that they do not support all the features that we will need. So we stick to Spark SQL, Presto, and Hive, and we tested one experimental solution, which is Hive together with Druid. It is a solution in which we create a Druid table and Hive table, and this Hive table is backed by Druid table. So we query Hive, and every simple query gets delegated to Druid, and if we want something more complex, it gets scheduled as MapReduce job, and we can compute it as well. And Hive was the worst. Spark and Presto did similarly, and we thought that they may require some further testing on a more distributed environment. And this Hive together with Druid was the fastest, but we've encountered a lot of known bugs in there, and it's not yet mature enough to be used in a big organization. So we decided to do distributed tests of it. We took the same query. The data set was the whole data for the time range that the query operated on. So we could compare those results one by one with Teradata, because assuming that we partition our data by date, even if we add a lot of more historical data, it shouldn't affect the performance of a query, as the query won't touch this historical data because of the partitioning. And we ran the query 3 times and took the best of it. We stored all of the results. We have them in our blog post. I will tell you something more about it later. And as a platform for testing, we've chosen Google's DataProc. It is a platform on top of Google Cloud in which you can you can easily set up cluster of any size with pre-configured Spark, Presto, Hive, and possibly some other big data solutions. It's going to be running within Google Cloud on virtual machines. And what was most important for us was that all the software is available in newest versions and is optimized to run with each other and for the hardware that they use. So there is no risk that we could potentially mess up something with configurations and discriminate one solution. And yeah, and it's gonna be easy to reproduce for anyone who wants to redo our tests later on. Okay, here are the samples of shell client that we've used, the Google's one. So basically we created a Google storage bucket, put all the data in different formats that we would like to benchmark. For us it was org and Parquet. And we created a DataProc cluster. We specified the number of working nodes, the type of them, and we've used 3 init actions. One is predefined for running Presto, because we needed to put it here because it's not started by default. Spark and Hive are there already when you run it. And 2 additional ones which we created on our own. One is for copying data from this storage bucket into local HDFS for this cluster, as it has slightly better performance. and the other one is for creating a schema out of this data. So when we start the cluster, we automatically run a script that creates a schema of this data, and we can query Hive directly, and other technologies may use Hive schemas for querying as well. And then we could SSH into this computing cluster and use Spark SQL client, Hive, and Presto in order to run our queries. More details can be found on our blog. We just published today the blog post about those benchmarks, so I encourage you to visit it. It's the topmost link in there. And if you have any comments, I would really appreciate that. Okay, so now about results. Once again, this is auto-generated query. It's not optimized anyhow. It's not optimal, and all of it was running in vanilla setups without any optimizations. And we see that Hive did terribly, ran over 200 seconds, and it didn't improve. We checked different versions of it, and every query was as slow as the first one. We've compared the Spark between 1.6 and 2.2 version, and it made a huge improvement from over 35 seconds every time to 4 seconds in Spark 2.2. And as for the Spark and Presto, they were comparable. Presto was a little bit faster when we ran first query, but then when everything got warmed up and some things got cached, they were similar, running below 5 seconds. So we can see that even on such small cluster and without any extensive optimizations, we could beat Teradata, which is an enterprise data warehouse. Here is funny thing. The cost of those tests at all was $14. As I said, we kept the clusters running for a small amount of time. So when we created the cluster, we ran a couple of queries for a few hours, then we shut it down. So we didn't have to pay a lot for it. And one more thing that I would like to share with you is that later on I've been doing some lecture for students, presenting this case and doing live demo of these benchmarks. And I forgot to shut down a pretty large cluster, and I left it running for over a month, so it consumed a lot of money. But yeah, that happens sometimes. But I written to Google support about what happened, and they after one day of investigation, they decided to not charge this money. So it's really great of them. And as for the cost of license, I cannot quote any concrete figure in here, but I believe that all or most of you work in this industry, so you may imagine how big those numbers can be. And that's it from us. Thank you very much.
Thank you, Grzegorz and Tomasz. Okay, questions?
Mm-hmm.
Or
We have one.
okay.
So I have a question about this trolley picking problem, and so basically I understand you try to minimize the congestion, but how would you like define it? I mean, you will have like two heat maps, and how you decide which of them is better?
Yeah. So first of all, we don't try to optimize congestion. We try to optimize peaking time, right? So this is the main goal, and the beauty is that the simulation, when it runs, you know, you can make it so that it actually tells you what is the picking time, because you have the move of every basket and you know how long it took to do the picking time. As for the congestion, I would look at it more as a you know, guiding thing. So if you visualize it and you see, okay, oh, maybe we should move it here, right? So so this is this sort of human-machine cooperation, right? It sort of shows you where the problems might lie, and then you say, oh, okay, yeah, let's rearrange it a little bit here and see what's happening. Obviously, that could be done automatically as well, this thing, but yeah. So this is where this congestion comes into place.
Any other questions from here?
So do you use the Google Dataproc in everyday use, like for generating reports and stuff like this, or only for special cases to analyze the whole data you have?
We've only used it for this particular benchmark. Normally we have custom infrastructure, but no, it may get some time to set up a test environment, to configure all of those technologies. So we decided to simply go for Google's infrastructure, and it was faster for us, and we were sure that we're gonna have it configured properly.
Did you thought about breaking the basket value when it comes to, I mean, I would like to have my high value baskets stay a little longer in my shop, and the low value baskets, I would like to make the flow very fast.
Okay, I understand. I don't think that was one of the criteria, because if you think about trolley picking in the warehouse, it doesn't really matter but the main case here was actually the warehouse. So in that case, you know, that scenario, it doesn't really matter, right? Because you just want to optimize the time people walk. In the store, as we were saying, you know, whether the store wants to optimize or minimize picking time, maybe not, right? Maybe you need to go around all of the valleys, right?
And for the customers that are actually buying few things, I would like
Sure.
to make them faster and leave the store, to leave it a little bit more space for the customers that are spending a lot. I would like to shop.
Yeah, exactly. That might be a good point. As I'm saying, in this particular case, there was a huge focus on the warehouse, not the store. But yeah, very good question.
All right.
So
I think
okay.
yeah, let's give a break, and
Yeah, we can.
you can catch
We can
these
take
guys
it
up
offline,
like
yeah.
during the conference. So thanks again, right, for a
Thanks,
great
guys.
talk.